Hello everyone and welcome to our channel Mootechie. It's wonderful to have you here as we dive into the fascinating world of emulsions. This is a topic that's all around us, from the food we eat to the lotions we use, so let's get started and uncover the science together. Now let's begin with the basics. The word emulsion actually comes from the Latin word for to milk, and that makes perfect sense, because milk is one of the most common examples of an emulsion we encounter every day. So what exactly is an emulsion? An emulsion is a mixture of two or more liquids that are normally immiscible. Now, immiscible is just a scientific way of saying they don't mix or blend together. Think of oil and water. They famously separate. But in an emulsion, we force them to mix and stay mixed. Moving forward, let's get a little more formal with our introduction. Emulsions are actually part of a more general class of two-phase systems of matter called colloids. The term emulsion is specifically used when both the dispersed phase, that's the tiny droplets, and the continuous phase, the surrounding liquid, are both liquids. You can find emulsions in so many everyday items. Think of a vinaigrette salad dressing you have to shake up, creamy mayonnaise, or of course milk. Even the photosensitive side of photographic film is an example of a related colloid system. Next, we explore the different types of emulsions. There are four main types we'll discuss. First, we have oil in water emulsions. Then, water in oil emulsions. We also have more complex multiple emulsions, which can be oil in oil, or water in oil in water. And finally, we have microemulsions grown, which are a special, clear and stable type. Coming up, we'll discuss the key differences between the two primary types. Let's clearly distinguish between oil in water, OW, and water in oil with O emulsions. In an oil in water, or OW emulsion, water is the dispersion medium, the continuous phase, and oil is the dispersed phase, meaning it's broken up into tiny droplets. These emulsions are non-greasy and easily removable from the skin with water. They're often used externally to provide a cooling effect, like in vanishing cream. For internal use, OW emulsions are preferred because the bitter taste of oils can be masked by the continuous water phase. In a water in oil or WO emulsion, the roles are reversed. Oil is the dispersion medium and water is the dispersed phase. These emulsions feel greasy and are not washable with water. They are used externally to prevent the evaporation of moisture from the surface of the skin, like in cold cream. So, WO emulsions are generally preferred for external creams. Now, let's visualize this with a simple diagram. Imagine two diagrams side by side. The first shows water as the main background, with tiny oil droplets suspended in it and an emulsifier molecule at the interface. This represents a water-based or OW emulsion. This represents an oil-based or WO emulsion. As we continue, let's understand how emulsifiers work. This slide shows a beaker. We have oil and water, and when we agitate them with emulsifiers, they mix. The illustration zooms in on an emulsifier molecule, showing it has a polar head, which loves water, and a non-polar tail, which loves oil. This structure allows it to act as a bridge, stabilizing the mixture of oil and water, forming an OW emulsion. Let us now look at a visual representation of the dispersed phases. Here we see two diagrams. On the left, for an OW emulsion, we see many small oil droplets dispersed throughout a continuous water phase. On the right, for a with O emulsion, we see many small water droplets dispersed throughout a continuous oil phase. Next, we delve into the more complex world of multiple emulsions. Multiple emulsions are like emulsions within emulsions. They are systems where the dispersed phase itself contains smaller droplets that have the same composition as the external phase. There are two main types. The first is oil in oil, or OWO. The second is water in water, or WOW. Let's understand these multiple emulsions in more detail. In an OWO system, an aqueous phase, that's a water-based phase, separates an internal oil phase from an external oil phase. Think of it as a water droplet surrounded by an oil phase, and that water droplet itself contains one or more tiny oil droplets inside it. In a WOW system, an organic or oil-based phase separates an internal aqueous phase from an external aqueous phase. So it's an oil droplet surrounded by a water phase, and that oil droplet contains one or more tiny water droplets inside it. These WOW systems are the most studied among multiple emulsions. Now let's look at a figure that illustrates these systems. This is figure 1, showing formulation examples. It depicts a single-phase system, an oil in water emulsion, a water in oil emulsion, and a more complex water in water triple emulsion. The key explains the symbols. Water is shown as a blue background, a water-soluble drug is represented by a blue dot, oil is a yellow background, and an oil-soluble drug is a yellow dot. This helps us visualize where different components would reside in each type of emulsion. This figure is credited to particle sciences. Following this, we'll discuss microemulsions. Microemulsions are clear, stable liquid mixtures of oil, water, and a surfactant, which is an emulsifier frequently used with a co-surfactant. Here's the amazing part. Unlike ordinary emulsions which often need vigorous shaking or high-shear mixers, microemulsions form spontaneously upon simple mixing of the components. The two basic types of microemulsions are, just like macroemulsions, oil in water and water in oil. So how are microemulsions different from common macroemulsions? There are three key differences. First, they appear as clear, transparent solutions, not milky white. Second, the diameter of the internal phase droplets is extremely small, ranging between 10 and 200 nanometers. And third, they are thermodynamically stable (unease), meaning they form spontaneously and remain stable over time. Now let's move on to how we can identify what type of emulsion we're dealing with. These are called detection tests. The first test is the dilution test. It's based on the solubility of the external or continuous phase of the emulsion. An OW emulsion can be diluted with water, because water is its continuous phase. A with O emulsion can be diluted with oil. The diagram shows this process. When an emulsion is diluted with water and shows no phase change, it's likely an OW emulsion. If it's diluted with water and shows a phase change, it's a with O emulsion. Conversely, if diluted with oil with no phase change, it's WO, and with a phase change, it's OW. Another important test is the conductivity test. Water is a good conductor of electricity, whereas oil is not. Therefore, if the continuous phase is water, the emulsion will conduct electricity. In the diagram, we see two beakers with electrodes. In the first, with an OW emulsion, the bulb glows because the continuous water phase allows current to flow. In the second, with O emulsion, the bulb does not glow because the continuous oil phase insulates the circuit. Next up is the dye solubility test. In this test, a water-soluble dye, like amaranth, which is red, is mixed with the emulsion and observed under a microscope. If the continuous phase appears red, then the emulsion is OW type because the water is the external phase and has dissolved the dye. If the scattered globules appear red and the continuous phase is colorless, then it is WO type. The dye has dissolved in the water droplets, but not in the continuous oil phase. The image on this slide shows an OW emulsion under the microscope after this test, with the continuous phase colored red. Let's look at one more test and then introduce emulsifying agents. The fluorescence test relies on the fact that many oils fluoresce or glow under UV light while water does not. Therefore, an OW emulsion will show a spotty pattern under UV light, only the oil droplets will fluoresce. A with O emulsion will fluoresce uniformly because the continuous phase itself is oil. Now this brings us to a key player, emulsifying agents. These are substances that are soluble in both water and fat. They enable the fat to be uniformly dispersed in water as a stable emulsion, preventing it from separating. Now how do we classify these emulsifying agents? They are classified into different types based on the kind of film they form. We have synthetic or surface active agents, natural agents, and finely dispersed solid particles. Let's look at a table. Type: film formed. Examples: notes, synthetic, surface active, monomolecular film, anionic, potassium laurate, sodium lauryl sulfate. Best at pH greater than 8. Cationic, quaternary ammonium salts. Works at pH range of 3 to 7. Non-ionic, polyoxyethylene fatty alcohol ethers, sorbitan fatty acid esters. Works in a wide pH range of 3 to 10. Natural, multimolecular or monomolecular films, hydrophilic colloids, acacia, gelatin, lecithin, cholesterol. Finely dispersed solid particles. Solid film, colloidal clays, bentonite, vegum, metallic hydroxides, magnesium hydroxide. Continuing our classification, we have natural emulsifying agents. These can form either multimolecular or monomolecular films. They include hydrophilic colloids like acacia, gelatin, lecithin, and cholesterol. The third category is finely dispersed solid particles. These form a solid film at the interface. Examples include colloidal clays like bentonite and vegum, and metallic hydroxides like magnesium hydroxide. Let's look at some specific products and their uses. Here's a table. Product: source/composition. Principal use: cetyl alcohol, chiefly C_16H_33OH. Lipophilic thickening agent and stabilizer for OW lotions and ointments. Methyl cellulose, series of methyl ethers of cellulose. Hydrophilic thickening agent and stabilizer for OW emulsions, and a weak OW emulsifier. Stearic acid, mixture of solid acids from fats, chiefly stearic and palmitic acid. Lipophilic thickening agent and stabilizer for OW lotions. Sodium carboxymethyl cellulose, sodium salt of the carboxymethyl ester of cellulose. Hydrophilic thickening agent and stabilizer for OW emulsions. Here is a broader list of common emulsifying agents. It includes agar, cholic acid, cetyl alcohol, albumin, diacetyl tartaric acid ester, casein, alginates, glycerol monostearate, egg yolk, gum, Irish moss, which is also called carrageenan, soap, monosodium phosphate, ox bile extract, and lecithin. Now, let's focus on one very important natural emulsifier, lecithin. Lecithin is a non-ionic emulsifier. It's one of a group of phosphoglycerides found in various plants and animals, including egg yolk, nerve tissue, semen, and cell membranes. It's a naturally occurring phospholipid derived from sources like soybean. The key to its action is that it's both oil and water-loving. Lecithin is also used as a vitamin supplement and a dietary supplement. Lecithin has some fantastic benefits. It's a most important component of our cells. It can help nourish damaged cells and tissues, and also helps in keeping skin soft and supple. It's used in making surfactants, to improve the flow properties of chocolate, curare paille, to reduce cholesterol levels, and it helps keep our blood's cholesterol circulating freely. Fundamentally, lecithin is an emulsifier or mixing agent that helps fat and water stay together. So where do we get lecithin from? Soybean and egg are excellent sources of lecithin. You can find it in many products like egg yolk, mayonnaise, ice cream, milk, cosmetics, lotion, cheese, margarine, and coatings. The image on this slide shows a jar of mayonnaise which uses an emulsifier like lecithin from egg yolk to keep its structure stable. Now let's talk about a very familiar emulsifier, soaps. Soaps or detergents can be anionic, cationic, or non-ionic. They are amphipathic, meaning one end of the molecule is hydrophobic, it sticks to oil, and the other end is hydrophilic, it sticks to water. A soap or synthetic detergent molecule contains a long non-polar tail and a polar or ionic head. The non-polar tail dissolves well in non-polar grease and oil, while the polar head dissolves in water. When you wash, the tails of the soap molecules penetrate into the oil or grease and break it up into tiny structures called micelles, which can then be rinsed away. Let's break down the types of soaps and detergents. Cationic detergents are often quaternary ammonium salts of acetates, chlorides, or bromides. Anionic detergents include sodium alkyl sulfates and sodium alkyl benzene sulfonate. Non-ionic detergents are esters of alcohols having high molecular mass. A common example is polyoxyethylene fatty alcohol ethers. Now let's examine another specific emulsifier, diacetyl tartaric acid ester or DATEM. DATEM is a non-ionic emulsifier. It's used to strengthen dough by building a strong gluten network, which is why it's very common in baking. It helps enlarge the physical volume of bread, improve the structure of its tissue, prolong shelf life, and increase softness and pliability. You'll find it in crusty bread, products with a chewy texture, biscuits, coffee whiteners, ice cream, and salad dressings. How does DATEM work? It appears to interact with the hydrophobic parts of gluten, helping the protein unfold and form a strong cross-link structure. It's used as an emulsifier and dispersion agent to improve the mixing between oil and water. It's dispersive in hot water, soluble in oil and fat, or some kinds of organic solvents. It's even used in butter to improve its taste. Moving on, let's discuss another natural category, gums. Gums can be cationic, non-ionic, or anionic. For example, xanthan gum is anionic and natural, cationic guar gum is semi-synthetic and cationic, and guar gum is non-ionic and natural. Gums are hydrocolloids that bind, thicken, and emulsify ingredients, especially in gluten-free products. Guar gum in particular is an approved emulsifier, thickener, and stabilizer for a wide range of foods, cosmetics, and pharmaceuticals. A great feature is that it thickens without the need to apply heat. Guar gum has many useful properties. It can act as a light emulsifier by preventing oil droplets from coalescing or merging. It's easily soluble in both cold and hot water, it's resistant to oil, greases, and solvents, it provides high viscosity, it's functional at low temperatures, and it's an excellent thickening agent. Its uses are vast. In baking, it increases dough yield. In dairy products, it thickens milk, yogurt, and liquid cheese. In meat products, it acts as a binder. It's also used in dry soups, sweet desserts, and frozen food items. As a water-soluble fiber, guar gum acts as a bulk-forming laxative case, so it's effective in promoting regular bowel movement and relieving constipation. You can find it in lotions, surfactant products, conditioners, ice cream, cosmetics, and baked goods. Now that we know how to make emulsions, what can go wrong? Let's talk about emulsion instability. The instability of pharmaceutical emulsions can be classified as follows: flocculation and creaming, coalescence and breaking, phase inversion, and miscellaneous physical and chemical changes. This slide shows a learning diagram illustrating the progression of instability. It starts with flocculation, where particles clump together. This can lead to sedimentation or creaming, where the clumps rise or fall. Eventually, this can progress to coalescence, where the droplets merge. Let's define these terms, starting with flocculation. Flocculation is the process where the small spheres of oil join together to form clumps or flocks. These flocks are larger, so they rise or settle in the emulsion much more rapidly than individual particles would. Next is creaming. Creaming is the concentration of the floccules of the internal phase, forming either an upward or downward layer. This happens based on the density of the internal phase compared to the external phase. If the droplets are less dense, they cream upward. If they're more dense, they sediment downward. The creaming process is described mathematically by the Stokes equation. The equation is, let's break that down. dx by dt is the rate of settling. D is the diameter of the particle. Rho_I and Rho_E are the densities of the internal and external phases. G is the gravitational constant. And eta is the viscosity of the medium. So what factors affect the rate of creaming? 1. Globule size. If you increase the globule size, the rate of creaming increases dramatically. 2. Density difference. Rho_I minus Rho_E. If the densities are equal, Rho_I minus Rho_E equals 0, then the settling rate is 0 and no creaming occurs. If the internal phase is less dense, you get a negative value and upward creaming. If it's more dense, a positive value and downward creaming. 3. Gravity, G. This is usually constant, but centrifugation is sometimes applied to accelerate the process for testing or separation. 4. Viscosity, eta. If you increase the viscosity of the medium, the rate of creaming decreases. Now let's look at a more severe form of instability, coalescence. Coalescence is the process by which emulsified particles merge with each other to form larger and larger particles. It's an irreversible process. The diagram illustrates this beautifully. You start with two separate liquid droplets, they make contact, a neck grows between them, and finally, they merge completely into one large droplet. This leads us to the most severe instability, breaking. Breaking is when, due to the combined effects of coalescence and creaming, the oil separates completely from the water. It forms a single continuous layer that floats at the top. The emulsion is permanently destroyed. Let's clearly differentiate between creaming and breaking, which is also called cracking. Creaming, breaking, cracking. Formation of an upward or downward layer. Complete separation of the emulsion into an upward oily layer and a downward aqueous layer. Reversible process, can often be redispersed by shaking. Irreversible. Shaking won't fix it. Partial or no coalescence of the droplets. Complete fusion or coalescence of the droplets. Another type of physical instability is phase inversion. In phase inversion, an OW type emulsion changes into a with O type, and vice versa. This is a physical instability, not a chemical one. What can cause it? It can be brought about by the addition of an electrolyte. For example, adding calcium chloride to an OW emulsion made with sodium stearate can invert it to a with O emulsion. It can also happen by changing the phase volume ratio, that is, the proportion of one liquid to the other, or by temperature changes. So how can we minimize phase inversion? We can do this by using the proper emulsifying agent in an adequate concentration. By keeping the concentration of the dispersed phase between 30 to 60%. And by storing the emulsion in a cool place. The diagram shows that further addition of the internal droplet phase can lead to phase inversion, changing the emulsion type. Now, let's talk about cracking in the context of preparation. Cracking can also refer to when an emulsion fails during its preparation. The primary emulsion doesn't become white and creamy but instead takes on an oily, translucent appearance. When this happens, it's impossible to dilute it with water, and the oil simply separates out. What causes an emulsion to crack? There are several reasons. 1. The addition of an incompatible emulsifying agent. For example, mixing a monovalent soap with a divalent soap. 2. The chemical or microbial decomposition of the emulsifying agent. For instance, an alkali soap can be decomposed by an acid. 3. Exposure to increased or reduced temperatures. 4. The addition of a common solvent that can dissolve both phases. Now that we understand instability, let's delve into the mechanism of how emulsifying agents actually work. When two immiscible liquids are agitated, one liquid is dispersed as small droplets in the other. To prevent these globules from coalescing, we need an emulsifying agent. These agents work by forming a protective film at the interface between the two phases. There are three primary types of films they can form: monomolecular films, multimolecular films, and solid particle films. This slide has a very helpful diagram. It shows the oil phase and the aqueous phase. In the monomolecular film, a single layer of emulsifier molecules lines up at the interface. In the multimolecular film, a thick multi-layered film forms. In the solid particle film, a layer of solid particles collects at the interface, forming a physical barrier. Let's explore each film type in detail, starting with monomolecular films. A coherent flexible monomolecular film is formed by surface active agents, SAA. This flexible film can prepare either OW or WO emulsions. Its key actions are to lower the interfacial surface tension and greatly increase the stability of the emulsion. Examples include potassium laurate and polyoxyethylene sorbitan monoleate. Next, multimolecular films. These are strong, rigid films formed mostly by hydrocolloids. They typically produce OW emulsions. However, they have a low effect on actually lowering surface tension. Their main strength is forming a physical, gel-like barrier. Examples are acacia and gelatin. The figure on the slide, labeled 2b, illustrates this multimolecular film at the interface. And finally, solid particle films. This film is formed by solid particles that are very small compared to the droplets of the dispersed phase. They can form both OW and WO emulsions. Crucially, the solid particles must be wetted by both phases to some degree in order to remain at the interface and form a stable film. Examples include bentonite, graphite, and magnesium hydroxide. Figure 2c shows a diagram of this solid particle film. The HLB system. Now let's introduce a very important system for choosing the right emulsifier, the HLB system. HLB stands for hydrophile-lipophile balance. It's a crucial concept for formulating stable emulsions. So what is the HLB system? It's a definition of the balance between the hydrophilic sadouce or water-loving portion of the molecule and the lipophilic sadouce or oil-loving portion of the molecule. The relation is straightforward. The higher the HLB number, the higher the hydrophilicity of the surfactant. A high HLB means it prefers water, a low HLB means it prefers oil. This leads us to a very practical table: HLB number versus solution function. HLB range. Solution function: 4 to 6. Water in oil emulsifiers: 7 to 9. Wetting agents: 8 to 18. Oil in water emulsifiers: 13 to 15. Detergents: 10 to 18. Solubilizers. So what are the uses of the HLB system? It helps us study the chemistry of surfactants. And it allows us to predict how a surfactant will behave in a formulation, making it easier to select the right one for the job. Calculating the HLB value. Now, how do we calculate the HLB value? One common method is the Griffin equation. The Griffin equation is where S is the saponification number of the ester and A is the acid number of the fatty acid. This is often used for systems containing ester groups. Another method is the Davis equation. The Davis equation is where HGN is the hydrophilic group number and LGN is the lipophilic group number. This method assigns numbers to different chemical groups in the molecule. Preparation of emulsions. Alright, now let's shift gears and talk about the practical side. How do we actually prepare emulsions? 1. Continental or dry gum method. 1. The emulsifier, often a gum, is triturated with the oil in a perfectly dry porcelain mortar. 2. Then, all of the water is added at once. 3. The mixture is triturated immediately, rapidly and continuously. You'll hear a characteristic clicking sound and see a thick white cream form. This is your primary emulsion. 4. Finally, the remaining quantity of water is added slowly to dilute it to the final emulsion. 2. English or wet gum method. 1. Here, you first triturate the gum with water in the mortar to form a mucilage. 2. Then, the oil is added slowly, in portions, while the mixture is continuously triturated. 3. After all the oil is incorporated, you mix it thoroughly for several minutes to form the primary emulsion. 4. Once that's stable, you add the remaining quantity of water to make the final emulsion. 3. Bottle or Forbes bottle method. This is great for extemporaneous preparation, especially with volatile oils or oils with low viscosity. 1. You place the gum and oil in a dry bottle and shake it. 2. Then a volume of water equal to the oil is added in portions, with vigorous shaking after each addition, to form the primary emulsion. 3. Finally, the rest of the water is added to make the final emulsion. Auxiliary method. An emulsion made by the wet gum or dry gum method can often be improved by passing it through a hand homogenizer. In this device, the pumping action of the handle forces the emulsion through a very small orifice. This drastically reduces the size of the dispersed droplets to about 5 microns or less, resulting in a much finer and more stable emulsion. Nascent method, or in situ soap method. This method creates soaps right in the mixture to act as the emulsifier. The two types of soaps made this way are calcium soaps and soft soaps. Calcium soaps form WO emulsions and are made from certain vegetable oils, like oleic acid, mixed with lime water, a calcium hydroxide solution. They are prepared simply by mixing equal volumes of the oil and lime water. Beaker method. This is the most appropriate method for preparing emulsions from surfactants or other non-gum emulsifiers. 1. You start by dividing all your components into water-soluble and oil-soluble groups. 2. Dissolve the oil-soluble components in the oil phase and the water-soluble components in the water phase using separate beakers. 3. Heat both phases to about 70 to the power of circ C over a water bath to melt any oleaginous components. 4. Then with stirring, add the internal phase to the external phase. 5. Continue stirring until the mixture cools down to room temperature. Uses of emulsions. Now that we know how to make them, let's explore the incredible uses of emulsions, starting in the chemical industry. Chemical industry. Cationic emulsions are valued for their antimicrobial properties. Non-ionic emulsions are widely used because of their low toxicity, their ability to be injected directly into the body, and their compatibility with many drug ingredients. Agriculture industry. Used as delivery vehicles for insecticides, fungicides, and pesticides. Using an emulsion allows these chemicals to be effectively diluted with water and provides improved sprayability for even coverage. Cosmetic industry. They allow for the dilution of active ingredients to a safe and optimal concentration. They are the primary delivery vehicle for many hair and skin conditioning agents. A classic example is hair conditioners. Surfactant technology. Emulsions offer benefits like reduced odor and flammability. They provide significant advantages over solvent-containing systems. A great example is in water-based paints and inks. Food industry. So many foods are emulsions. Milk is a naturally occurring emulsion. Others include salad dressings, gravies and other sauces, whipped dessert toppings, peanut butter and ice cream. Fire extinguishing. Certain emulsions are very effective at extinguishing fires on small, thin layer spills of flammable liquids. Pharmaceutical applications. Emulsions are fantastic in pharma for many reasons. They can cover up unpleasant tastes of oils. They can increase the absorption rate of drugs. Topical emulsions are easily washable. They can be formulated to have an acceptable spreadable viscosity and are less greasy than pure ointments. They can be designed for controlled drug release bioavailability. They can protect thermolabile drugs sensitive to heat. And they can help reduce variability in how different patients respond to a drug. Storage and packaging. Finally, we must discuss the important topics of storage and packaging. Containers. For oral use, they are usually packed in well-filled bottles with an airtight closure. Light-sensitive products are packed in amber-colored bottles to protect them. For viscous emulsions, wide-mouth bottles should be used for easy removal. Labeling. The label on the emulsion must always mention that the product has to be shaken thoroughly before use, due to potential creaming. Products for external use must clearly state for external use only on their label. Storage temperature. Emulsions should generally be stored in a cool place. However, refrigeration should often be avoided, as this low temperature can sometimes promote instability or cracking. Thank you. See you in the next class.